Alright, this is part B for chapter 3, probably the most abstract section for ACE chemistry. We're talking about where electrons are located and specifically into their atomic orbitals. So basically you have your electron cloud, and electron cloud is filled up with energy levels. That's the principal shell. So rho 1 is 1, rho 2 is 2, and so forth. And then within the principal shells, there's subshells of S, P, D, and F. And then within each subshells, there are orbitals that are related to those subshells. And those are specifically shaped where the electrons are located. So in your principal quantum shell, each has different number of subshells. So like energy level 1 has one subshell, 1s, and then energy level 2 has 2p, or 2s and 2p, and then 3 has 3s, 3p, and 3d, and then so forth. And then the orbitals are within the subshell. So within the s orbital of the subshell, there's the s orbital. They're basically the same because it's one shape. But when you get to the p and the d, the p's are broken down into three different orbitals: px, py, and pz. Those are based on the plane they're on, the axis. And then the d has 5 different orbitals within the subshell of the d. The most energy is in the f. So the least amount of energy of electrons is the s, and then it goes to p, d, and then f. The maximum number of electrons that can hold into each subshell is 2 for the S, 6 for the P, 10 for the D, and 14 for the F. And after the argon, subshells don't not necessarily fill in the SPD orbital, starting with potassium. So you can see the periodic table basically follows along the subshell. So the first energy level is 2s, holds 2 electrons because there's only 2 elements, hydrogen, helium. Then in the second energy level, you have the 2s and the 2p. The 2s fills the lithium and beryllium, and then there's 6 elements to fill the 6 electrons for the p. The same thing for the d, and then starting with scandium, you start filling in the 3d and the 3d. The F doesn't start till you get to the lanthanide actinide series. So, first energy level, the first subshell is S, which is the same as the orbital, holds 2 electrons, and then the second energy level holds a S subshell and a P subshell, giving you a total of 8. And then the N for 3 gives you 3 different subshells of S, P, and D, 2 for S, 6 for P, and 10 for D, as you can see there. Alright, each subshell contains one or more atomic orbitals. So that's the actual shape of the where the electrons are located. The region around the nucleus can be occupied by one or two electrons. Each orbital can only hold 2 electrons max. So, in the s orbital, you can hold 2 electrons. That's why it's always helium and lithium, hydrogen, and helium, and then all the alkali and alkali earth metals are always S. And then the P can hold 2 electrons for the X, the Y, and the Z. That's 2, 4, 6. That's why it's 6 electrons in total for the P subshell. Here's more drawings that you could be asked to draw. It basically looks like a dumbbell or an infinity sign for the p orbital. It depends on the axis is whether it's x, y, or z. Here's some more shapes. You can see the one S only has one subshell because, or one orbital, because it only holds 2 electrons. Then the 2s, you can see the 1s in the middle, and then the 2s in the white. And then you have the 3p orbitals, x, y, and z. So how do you know the configuration? Basically, you draw a table, 1s, 2s, 3s, all the way to 7s, and then you go 2p all the way down to 7p, 3d all the way to 6d, and then the 4f, 5s. So you go from right to left, drawing an arrow. So it goes 1s, then it goes 2s, then it goes 2p, 3s, then 3p, 4s, then 3d, 4p, 5s. So you have basically just a diagonal going from right to left. Alright, name the three types of orbitals present in the 3D principal quantum shell. That's n equals 3. So we have the 3s, the 3p, and the 3d in the n quantum shell. N equals 3. State the number of electrons found in each subshell. So you can hold 2 electrons in the 3s, you can hold 6 in the 3p, and then you can hold 10 in the 3d, a total of 18 electrons. 2 in the s, 6 in the p, 10 in the d. Alright, so how do we write configurations knowing that information? So we have electron configuration, basically says where each electron is located for each element in that specific case. The one in front is the shell, the energy level. The subshell is the S, and then the number of electrons in that subshell is the superscript. So for helium, with 2 electrons, you have 1s2. It's in the first row, so it's 1. It only is in the s, and it holds 2 electrons, so it's 2. Now lithium starts with the first row, so it's 1s2. But then, once it goes down to the third electron, it's in the second row, so it's 2, and it's in the s orbital, and it has 1 electron to give you a total of 3. So the superscripts have to equal the total number of electrons. Here's some other examples in your text. You can see as you add up the number of electrons, the superscripts, they'll give you the total number of electrons of the neutral atom. So a carbon has 6 electrons, that's 2 in the 1s, 2 in the 2s, and then 2 in the 2p gives you 6 electrons. There's some anomalies that haven't really been totally 100% proven, but chromium and copper are 2 of them. Chromium will go into the D before the 4s is filled. Same thing with copper. The 3d gets filled before the 4s gets filled, even though the 4s should have a full orbital compared to D. This is checkup number 6. Provide you some examples of electron configuration. So for 16 electrons, 9 electrons, and 20 electrons. So for 16, again, you just gotta make sure the superscript is equivalent to 16. So you go in order of 1s2, 2s2, 2p6, 3s2, and then there's 4 left over, so it's 3p4. And then for 9, the 1s and the 2s are filled, and that leaves 5 for 2p. And then for 20, all the way to the 3p is full. And then for calcium, it would be left with the 4s with 2 electrons, and 2 would give you a total of 20. Sometimes they use noble gas configuration to understand that you don't have to write everything out. Most cases, ACE will require you to write the whole thing out, but argon is used a lot because it fills all the way up to 3p6, and then you can see for after argon, you would just have like 4s1 or 4s2. For potassium, it would be 4s1. Now, once a S is filled, it actually goes to 3D, because 3D is just a little bit lower in energy than the 4P. So you gotta remember that aspect. Some anomalies in the S and the D. So in chromium and copper, you notice that they are both at 4s1. And there's really no scientific proof of why they act that way. It's just been understood that that's how they behave. So some things you have to remember about chromium and copper. But most cases they do go from the 4s gets filled and then the 3d and then it goes to the 4p after that. You can see in gallium, which is after zinc, it goes to the p orbital because it's in the p block. Same with bromium and krypton. So find the configuration for the following elements. So vanadium, copper, and selenium. So for vanadium, again, the 4s gets filled first for vanadium and then it leaves you with 3d. Sometimes the d is after the 4s, but it doesn't really matter. Copper is that rare case where d gets filled before the 4s. The electron jumps from the 4s to the d. And then for selenium, it's in the p block, so it has 4 electrons in the p block, so it's a 4p. So we talk about blocks. The S block is the alkali and alkali earth metals. The D blocks are your transition metals, and your P block, besides helium, are the last 6 row columns. All right, homework question. Write the element for that configuration that has the final configuration of 5s2, 5p6. Again, it ends in P, so we should be looking at the P block. And then the configuration for 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. Filling the orbitals. So each subshell has orbitals. We talked about the s and the p mainly. So in this case, boron has 5 electrons, so it's going to have 5 different electrons with opposite spins in each box, ending in the 2p. So for carbon, you write the configuration. You know it's 1s2, 2s2, 2p2. So 1s goes up and down, then you go up to 2s, that gets filled, and then in the 2p you have to switch boxes because they are opposite charge or like charges, so they're going to repel each other. So they're going to go into a px and a py. So for nitrogen, the same idea. The 1s gets filled first, the 2s gets filled, and then the 2p's all have a single electron in each orbital because they want to be further apart from each other. Oxygen, same thing. 1s gets filled, 2s gets filled. You put 1 in each box, and it leaves you with 1 electron, and that's when you have the opposite spin in one of the orbitals. In this case, in the 2px. Configuration of ions. So ion just means that they're going to gain or lose electrons. That means the number of electrons are going to change, and that means either taking away some of the orbitals or adding some. So sodium is a 1s2, 2s2, 2p6, 3s1, and if it becomes a +1, it loses 1 electron. So that 1s goes, the 3s goes away, and you're left with the p block of 2p6. Sulfur, we know, is ends in a 3p4. So it's going to gain 2 electrons, so that 4 turns into a 6. It has the same number of electrons as its noble gas in that family, which is argon. So that's considered what they call isoelectronic, where they have the same number of electrons but are different elements. One tricky thing about the ions for the the transition metals, that the 4s does get filled first, but they do lose their electrons first, mostly based on size. But so for titanium, we know it's a 4 electrons in the 4th energy level, so it's a 3d2, 4s2. It's going to lose 2 electrons, so it always loses from the s first. So that 4s is gone, and you're left with a 3d2 at the end for titanium, +2. write the electron configurations for the following ions. We have aluminum, oxygen, iron 3, copper 2, and copper 1. So for aluminum and oxygen, they both are isoelectronic to each other because they have the same number of electrons. Aluminum loses 3, but oxygen gains 2. So they both have the same number of electrons with the same configuration. And in both C, D, and E, iron, copper, and copper 1, they all lose from the 4s first, and then they lose, go from the D after that. So for copper 3, it loses 1 from the D. For copper 2, it loses 1 from the D. And copper 1 just loses 1 from the 4s. Alright, if you have any questions, we can cover that in class and work on that further.